So again, looking at patient birdcage coil, and also looking at leads. So we have an induced, we have a voltage drop across a lead that's exposed to a magnetic field. There's a current that's induced due to that. What kind of heating occurs, at the end of that lead? So we can predict that. Also looking again at the patient going now, we're looking at the heating in the body as the patient goes through the birdcage. And then finally, we're verifying that the heat's going to the right place in the region of the tumor. For the orthopedics industry, you can think about, really this slide here speaks to surgical planning. So having the ability to have the right material model. So I mentioned before we need the right material model description of how your material behaves. So in this example, we want to make sure we have soft tissue models that can handle the deformation of the skin properly and how it responds to an implant. On the bottom, I kind of went through the workflow already of taking a patient-specific bone. So imagine, the one thing I didn't describe as a process, I can describe that now. So for taking any medical scan, it's a series of slices through the body. I have 5? Down to 5 already, okay. Okay, you got a series of slices through the body. There's software out there. It's not our software, but there is software available for extracting geometry from that medical scan data. Again, we can extract the bone material properties from that medical scan if it's the right kind of scan, combine these two, and even combine that patient-specific model with a implant, and then start to analyze, and then I don't show it here, but also optimize the implant location such that you get the right performance. And in the case of these minimally invasive implants, you want to look at things like sliding distance. So it turns out metal sliding on bone isn't very comfortable. So we want to minimize that. We want to look at the stresses. For performance of the implant itself, what are the stresses on the prosthesis, the smaller stem going into the head of the femur? And then finally, what stresses are we going to see, or strains are we going to see in the bone? And just make sure that we're not affecting the overall physiologic milieu too dramatically. This is a slide that we already saw. So I meant to mention this at the beginning of my talk, and I forgot to, that this talk here also is really just taking one slide from Kevin Yallop's earlier talk, just blowing out into the 15 minutes or however long they'll let me talk. Anyway, so this is a Twincer dry powder inhaler. This was designed to be a disposable or easily reusable inhaler. It's really a self-actuating inhaler. So there's no moving parts in here. You have a drug reservoir here. You place the drug inside. The patient pulls in on a mouthpiece on the other side, and that intake by the patient activates the whole system. So you see the airflow paths through the different regions of the inhaler. What we look at with the simulation is making sure there's no dead zones. We don't see dead zones in this area or anywhere. We want to see nice even flow going over the drug package, et cetera. And something we always like to harp on it, at least whenever we can, is validation. So they did some analysis of just pressure drop as a function of flow rate through the inhaler, and we were able to match the experiments in green with the CFD predictions, which are the blue dots. I'll move a little quicker here, but we were also able to do the drug particle transport itself and show how, as you go above a certain critical diameter of particle, those particles will be trapped within this region here. So this says a lot about, performance. What size particle will you be able to handle with this type of inhaler as it's designed today? So if you really do need to get a 10 micron tends to be the limit. If you want to get to the deep lung, 10 micron, really you want to be around 8, 5, 6 microns, somewhere around this range or lower. That's what's going to make it to the deep lung. So the fact that these particles are getting trapped here maybe isn't a big deal for the drug delivery itself. Yeah, this is what you can understand with the simulation, is how the drug particles are responding to the flow. We can also hook up respiratory simulation to, again, detailed physiologic models. So in this case, getting the upper, really a nasal model from a medical scan and connecting that all the way down to the upper airway of the lung. So going down maybe 4 or 5 generations into the lung and looking at, what are the drug delivery patterns like? Where are particles deposited under normal conditions? So in this case, what we did is really seed particles on the outside of the nose. This truly isn't a drug delivery simulation because you usually don't have your face in a cloud of drug, except maybe some kind of a nebulizer or something. So in this case, really it's just seeing where particles would go if they were external contaminants or something. And looking at the difference in deposition patterns, and I can show it on this next animation here, which should be playing. Well, this one's not playing, but anyway, it'll show the difference. You can kind of see it here, how the larger particles will get stuck, more of them get stuck in this upper airway, and you won't see that the larger particles down here. So it's all blue down here. Many of the red ones are getting stuck in the upper airway. Okay, we can also do explicit analysis. So by explicit analysis, that's usually very short duration events or events where there's large deformations in your geometric model. So I just showed one here real quickly of a kind of really old school kind of PDA falling on a surface, battery cover falling out, batteries falling everywhere. These really short events, that takes a very specific kind of solver to solve that. And we do provide that as well. And obviously, Viet has that capability. Another one is for large deformation. This is called an endostaple. And tell me this, please. Sorry, guys. This one here, in fact, it's really interesting. It's a really neat simulation that wire, this even worked yesterday on the WebEx, sorry. The wire unrolls, and then you feed it through the vessel wall, and then you remove the guide wire that wire is mounted on, and the whole thing just goes back into its native conformational state. The last area is microfluidics, which I think is an area very exciting here at ACAMP. Just to move quickly, I'll talk about a few applications. One related to electrohydrodynamics, where you have a voltage drop driving the flow, and then neutral hydrodynamics, where the EHD part isn't coming into play. You either have pressure drops or surface tension driving the flow through the system. For the case of EHD, here we're talking about electrophoresis. So you have a voltage gradient. In this case, the voltage gradient is going from this side arm to that side arm. These are kind of in float here, and basically balancing out the flow and keeping flow from going to the upper and downstream side arm. And what we're doing is dispensing an analyte into this region here. So the geometry of this region between the two side arms is deciding how much sample is dispensed. Then we can switch the voltage drop to go from basically the east to the west side arms, and do a separation. Now we're seeing separation based on charge. Okay, so we have a low charge, charge equals 1 compound, a charge equals 2 compound, and the charge, one with the higher charge is moving twice as fast as the one with the lower. I just have like 2 slides, I think. So. Next is mixing. So we can look at passive mixing. In this case, we have what's called a herringbone mixer. The idea here is that you're introducing changes in the flow patterns as you move axially down different sections of the chamber. So you can see here an outline of what the flow patterns look like at each point in the channel. So whenever you have flow patterns that change axially as you move through a channel, what that's going to do is cause, say a particle's in the middle here and it's going to see a kind of downward flow going in this direction. Then it's in the middle here and suddenly it sees a different flow pattern. So it's going to go a different direction. So this is one way to induce very rapid mixing as you go down, for example, in a microfluidic system where you don't have turbulence basically to help you out. And we did some analysis of this. This is work I actually did with a high school student a few years back. And we were able to show things like nice matching between the experimental flow mixing pattern and the mixing pattern you see, and we predicted in Fluent, as well as then looking at mixing rates and how geometry can affect those mixing rates. And then the other side is active mixing, where now we require some kind of energy input to make mixing happen. In this case, we have a round cylinder in the center. It's moving, it's accelerating and decelerating very quickly, accel, decel. We have a simulation here that shows the streamlines. And during the acceleration and deceleration phase, these streamlines hardly change. They really change very little at all. In spite of that, it turns out you can get very good fluid mixing into the cavity. This is basically my PhD summarized in half a slide here, which I never thought I'd be able to do. But the nice thing is we did some simulations here, and we're able to show, basically predict from the simulations where are the isolated flow regions, where are the poorly mixed regions that are called islands in the flow. And this was like the greatest day of my life when I was able to just take those simulations that we ran. This is with a code that's just before Fluent, which is what we sell now. It was a code called FIDAP that was also owned by our company. But man, I just overlaid them, perfect match. It was beautiful. And then we could look at mixing rates as well.